Yeah, thanks for the invitation. I'm a PhD student at the University of Hamburg, specifically at the Observatory of Hamburg. And at this moment, I'm in Nordita visiting Axel, where we have been working on the radiation module and trying to incorporate it in our model. So as Piali already said, there were some bugs in this module that we have fixed, and I will be talking about that. The way I will do this is by telling this story mostly in a chronological order. Okay, so first a bit of background motivation. So what I'm showing you here is the energy equation, which is more or less the standard form that is usually used in convection, stellar convection specifically. Jordan already talked about this a few hours ago. And in this equation here, what you see is the radiative flux and a sub-bit scale flux, which is used to damp entropy fluctuations in the grid scale. Also, there is a heating and a cooling function. These two terms here are more specific to the model that's called star in a box, where there is literally a star embedded in a Cartesian box. And we solve the MHD equations in this box. So this is also just to give you some sense of how the simulations look like. These are three slices at the equator of the azimuthal component of the magnetic field. And as you can see, there is some evolution of the magnetic field. Okay, so usually the way that this equation is solved is by modeling radiation with the diffusion approximation. And where lately it has been more or less standard to adopt the Kramer's opacity with indexes of A equals to -1 and B 7/2. And we want to replace this scheme with the radiative transfer. So ideally with this, we will self-consistently create a surface as a function of opacity. And with that, we will have a photosphere. And we, of course, want to eliminate this cooling function and let the system cool with by solving the radiative transfer equation. Okay, so the first tests that we ran here was with 2D convection. So this is basically a slice in the equator of the star in a box setup. So just the convection there is no height. This is already with a cooling function. So we haven't fully eliminated the cooling function yet. The radiative flux is on the left plot and the radial velocity in the right. So the velocity looks similar to what you would expect to find. So there are upflows in this warm color and downflows in the blue color. But as you can see here in the left panel, there are some structures that don't look right. Specifically, they are the same number as the processors on each direction. So 8 in this specific case, 8 on the X direction and 12 on the Y direction. So you can already see that there is something wrong here, but this is most striking when one removes the cooling function. The radial velocity looks completely wrong. This pattern is strongly imprinted on the flows. And it might seem that the radiative flux, it's fine, but actually if you increase the contrast here, there is also very clear that there is some issues here. So at this point, we decided to take one step back and just go to 1D tests. we use the same setup as in Barakat and Brandenburg 2014, which is basically that you start with an isothermal initial condition, and you let the system cool by itself, and you maintain the temperature at the bottom. So if you do this in the set direction, then everything works fine. You see that there is some, after a few time steps, you develop an isothermal surface. But in the X and Y directions, there is no cooling. So these simulations here were evolved for the same time, but there is basically no cooling on the X and Y directions. So there is clearly a problem here in these two directions. Okay, so to understand what was happening here, it's good to take a look to this paper, Heinemann et al. 2006, where the
Felipe, you mentioned that this is, you are showing a 1D test, right?
Yes.
Yeah, so here, what do you mean by X parallelization, Y and Z? I mean, it is only along Z or X, or it is a...
Yes, so it means that, so for example, in this set direction, you choose any number of processors only in the set direction, and then the rays are also in the set direction. Then you do the same simulation, but on the X and Y directions. So it's basically changing the processors.
You're essentially orienting your axis along either X, Y, or Z alternative.
Exactly. Yes. Yes.
Thank you.
I think the question of Piali is also, if this is this the problem of the polarization, or is this just a problem of the direction?
No, it's only the direction. Yes. So yeah,
just direction. So, has nothing to do with the polarization. Okay.
Well, I think that it also has to do with that, because there was some issue with the communication along these two axes, but it's only related to the radiation module actually.
But it is, as you will probably show in a moment, a problem with the parallelization in the X and Y directions. So the parallelization in the Z direction was always okay. It's only that there's something wrong, something wrong in the X and Y parallelization.
Yeah, but if you would do the same thing in with one processor, and you do it in X and Y direction, would
I don't think then there was a problem.
Yes, no. I think that there is no problem there, because the problem is between the communication between the two processors when they were transmitting information about the arrays.
Okay, I understand. Thank you.
Yeah. Okay, so the way that this is described in this paper is that basically the equation that you work with is the cooling equation, and this is split into two parts. One that is called the intrinsic solution, which is valid within each processor, and then one part that needs communication. So Q here is cooling, tau is optical depth, and S is a source function, and I is the intensity. So there is only one part that requires communication, which is related to the boundary conditions, and also this Q0, which is initial condition of the rays. Okay, so this is what I will illustrate now. This is all in the paper of Heinemann again. So this is the processor layout. So yes, 2 by 2. And this is the direction of the rays. And as I said, Q0 is the cooling rate on the local upstream boundary of a given subdomain. So first, the processors take care of their intrinsic solution. This is done in parallel, and they assume that there is a vanishing cooling rate at the boundaries. Next, the local boundary rates are calculated where the rays hit. So these 4 phases here. Then, yeah, okay, let's go back. So now the processor 3 has the 2 upstream boundaries. These are calculated now. These are correct, and now it can work with the other two sides. So this is basically adding this extra term here to the intrinsic solution. Here, tau 0 is the optical depth in the ghost zones, and Tn is the optical depth of the corresponding boundaries of the processor. Now that these 2 are calculated, these are correct. Now it can transfer the information to the processors 1 and 4. So this would be the upper and right boundaries respectively. And these processors then can do the same. They have all of the correct cooling in their upstream boundaries, and then they communicate. They can calculate the other cooling rates. And this is then communicated to processor 2. And then after this is all set, every processor now can work in parallel and add a final correction term to all inner points in the subdomain. So that the scheme is quite simple, but the problem is that this is not what the code was actually doing. At least not in the X and Y directions. And this dates back to a commit in May 2006, or it may even be even further back. So what happened here is that the radiation rate module used to be split in 2. So there was one specific module that took care of the periodic boundary conditions. So for example, one of the issues here is that, so as I showed you in this 1D test, that there was no communication on the X and Y axis. And this can be also seen in this subroutine. So this is already in the old code. So this function, this subroutine here sets the physical boundary condition on the set X plane. So it needs to ask for the state of the rays on the Y direction, because those are the rays that are hitting these planes. But as you can see here, it was actually asking for the boundary conditions of the rays on the Z direction, and instead it should be asking for the rays on the Y direction. And this was the same for rays on the X direction. So in the YZ plane. There were also some other issues that there was no communication along X and Y. So there were some routines that were missing. So this was actually not hard to fix, because you only had to copy these routines and just change the indexes. So same as in here, basically changing Z by Y and X. So now that we fixed this, then we go back to the same setup that I showed you before, this 1D tests. And as you can see here, now X, Y, and Z produce the same solution. And I even had to exaggerate the width of the lines because they lie exactly on the same place. So we go back to 2D convection, and we want to make sure that it's also working in 2D. So again, in Y and X, radiative flux is on the left and radial velocity on the right. So this is without the fixes. Now, and also with some specific value of opacity, of kappa. Now the same setup without the, with the fixes now looks like this. Now the flow still looks completely wrong, but now with these fixes, we know that we were using the wrong opacities. Now this, call it 2D star, was optically thin everywhere. before these fixes, we thought that we were in the correct parameter regime, that we were using the correct opacities. But now, with the correct opacities and with the fixes, we get something that's much closer to what you would expect. So the radiative flux, it's clearly leaving the star at near a radius of 0.8. And also the radial velocities looks much more healthy. This is also seen now in 3D. This is some plots I made a few hours ago. This is the same setup, but now with the vertical direction included. Yeah, so in this plot here on the right, I'm showing you the optical depth, which is the solid lines, and the temperature, which is the dashed dotted line with 3 different opacities as a function of the radius of the star. And you see here now that well, this line shows the transition from optically thick to optically thin. And then these stars now are becoming optically thin around 0.9 or so. And also there is some tendency to develop isothermal layers in the outer regions. So it looks now that this has been fixed, because the 1D runs produce the same result independently of the directions of the ray. And also the 2D and 3D runs of stellar convection show a pattern that it's actually found in simulations that don't use the radiative transfer equation, but actually the diffusion approximation. Now there are some, of course, maybe.
Can I ask one question? So yes, what about now the difference between the solid and the dashed line? What is correct and what is not correct?
No, actually this is our two, both are correct. It says that the solid lines is the optical depth, and the dashed lines are the temperature.
Oh, okay, so sorry. Okay, now I understand. Thank you.
Yes, okay. So if you were using the radiation ray module, maybe you are asking if these changes will affect you. And I think that if you were using rays in the Z direction, then probably not, because what we found is that everything was coded to work on this direction specifically. There were some routines that, or yeah, some routines that were copied and pasted, but the last step, that's of changing Z for Y and X, it was not done. So then if you were using the X and Y direction, then yes, these results will affect you. And I think that it's better to rerun one simulation to confirm and to assess the damage. And so, as I said, the 1D solutions now are consistent, and the 2 and 3D simulations of convection now produce flows and optical depth that will look reasonable. So yeah, thanks.
I think there's a few questions.
Thanks, Philip. We have 2 questions. Yeah, John, we can ask.
Hi. Very nice work. Now that's very nice that it's now worked. So I have one question. Maybe Axel can answer, because I remember that in Atefe's master thesis, at the end there was one plot where you actually run convection with radiative cooling, where you're not using then well, it's 2D, but you were not using then many processor or more than one processor in the Y direction. So why was not seen it there? That was maybe a question to Axel. And then to Felipe a bit more. Yeah, maybe you can show.
So you're referring to these, right? Yeah.
Yes, but for you a question. So is there a plan? So at the moment this is all gray atmosphere.
Yes.
You have a plan to extend it to non-gray? So use some opacity tables or something like this?
Yeah, I think that's that's the goal here, because I'm mostly interested in modeling endorphs, and there are all sorts of molecules there that contribute more to the opacity. I think that especially in these cool stars, those are more important. I think that in the sun, it's H minus the principal contributor to opacity.
So you're planning to put this in, like, okay, that's very cool. Okay, great, thank you.
Axel, you can ask.
You're muted, Axel.
Oh.
Yeah, thank you. Yes, first a comment to the non-gray thing. The non-gray is implemented as a loop at the moment, so you can run a loop. I did some exploratory experiments at some point. It is in some sense quite interesting because you have different optical depths at different heights and stuff. And of course you have source functions that are also different. So all of that is maybe interesting to study, but it's in principle ready. Or it has. I have used it, but not really for production runs. And somebody else was actually talking about this. Maybe I forget now who it was. Or was it actually Felipe or yourself? Somebody I talked actually within the last week or so.
I think Shohel maybe, right? You were asking him if...
Sharon, yeah?
Who?
No.
No?
I think not.
No, Shohel.
I don't know.
Shahil, yeah, maybe Shahil was the one who, yeah, exactly. Good. So then there was the other question why it was not noticed before. So in principle, I did notice it actually, and simply didn't know what to do, right? So in some cases it showed up so that I did notice this, and there were many other cases when it didn't show up so much. And then I was sort of happy for the time being. So the problem, of course, appears if you really have. So, for example, the diffusion was actually working within one processor, right? So maybe you should have shown such a plot. It would have been nice to see such a plot where you see these. Actually, if you have the paper open, the one with Heinemann. Maybe you can show that. There was pieces. Do you have that?
So this problem was there even without parallelization.
So this one.
Right?
What did you say?
This problem was existing even without parallelization in X and Y.
No. No, it has nothing specifically to do with X parallelization as opposed to Y. It just has to do with any non-Z parallelization. And so the communication was really not done. So we reproduced, I mean, there's, by the way, a switch in the code where you can switch off communication. This was, of course, an interesting test. So we noticed then that if you switched off the communication, there was no difference. And then the result looked like Felipe is showing here, like these third and fourth panel. So we saw pieces of the thing that were completely smooth, and they were disconnected, connected simply by these jumps. But in between, it was completely perfect. So therefore, it was leading to a smoothing in the horizontal direction, except exactly on the boundary points. And so sometimes this showed up as a problem, but in many cases it didn't show up as a major problem. So I've done a lot of convection simulations, and in some cases it did show up, but not always, because most of the time the horizontal diffusion is not really that critical, of course, compared to the vertical one. But now when we have this star in a box, it's very important, of course.
Yeah, so something that I also noticed is that when you have a cooling function, then this processor pattern is less visible. And also with increasing opacity.
Yeah, right. So that was, of course, the other problem. So we were, of course, in the beginning, not really sure what is the right opacity to be used for the star in a box. And so we had for several experiments completely wrong opacities. And then this problem showed up extremely dramatically. In fact, let me then come back to this, and that's my last point. Can you show in your talk this picture again, where you had the temperature and the opacity? Right, exactly. So I would have thought that optical depth of, so how did you define tau? Did you define tau by just Q times rho times Q?
Yes.
Multiplied by the mesh size, perhaps, right?
Yeah, I'm iterating from the center to some.
So you did integrate. So is it
integrated?
Yes. So it's integrated, not non-integrated.
It's integrated.
But then the level 1 should really be the surface, and so it's surprising that the temperature becomes constant, actually only further out. Yes.
Yeah.
Right.
Around here.
So maybe that's not quite as I would expect that.
Yeah, maybe we still need to change the
maybe it hasn't run long enough or something yet.
Yeah.
And is there a mask? The mask is now turned off or not?
Yeah. Now yes, there is no mask now. This cools by itself. I mean, this is just self-consistently reproduced.
It's very sharp. The opacity, of course, very sharp. Yeah. I mean, maybe right. Okay. Anyway, Petri has a question now. Thanks.
Yeah. Thanks, Edson. Petri, you can ask now.
Okay. Yeah. Very impressive work. Especially in view of that we talked just a couple of days ago and then you still had some issues.
Yeah.
So very impressive indeed. The question I had was that have you handled how much more computationally intensive these runs are compared to the ones where you don't have radiation? And maybe it's also worthwhile checking the scaling behavior of the code with the radiation turned on.
Okay, so about the computational time, so these are 3D runs, and I didn't evolve it for too long. I think I'm using here 288 cube simulations, and these are without magnetic fields, and it takes very short time to reach some saturated regime.
So you use, by the way, 6 rays, or do you use now 8? Oh, sorry, do you use 26?
In these 3D runs, I think it's 18.
Oh, that's maybe another weird thing. All right. So maybe you need to check that because it should in principle use 26. And it could well be that it is indeed using 18 or 22. I would have actually guessed it was 22 when you use maximum. When you put this RAT2 max equal to 2.
Yes, it's 2. So yeah.
Then you should ideally use 26. And I thought you use actually only 22, but maybe it's really only 18. Do you think it's 18?
Yes, I remember seeing that was 18 in total.
Okay, yeah. So in any case, I think the most important rays are the ones in the coordinate directions, but having a few extra ones in the diagonals is of course nice. And then we should check that further.
Okay.
Yeah, I had a question. So about this number of rays. So what is of course, I mean, the optimal number of rays would depend on the problem, but I mean, for 2D or 3D, what is the optimum number of rays that one should use with this setup that you are using? Like, is 8, I mean, for example, 3D is 6 enough, or you should go beyond that? And you know, what is the difference? What difference does it bring?
Yeah, so I think that, well, ideally one would use like, the maximum amount of rays. The problem, of course, is that I have these spheres embedded in a box, so there is only a limited amount of directions that I can use. In these 2D runs in specific, I can use 8 rays, so in the corners and also on the sides of the box. And yeah, in 3D that number increases. I don't really know what's the what's the maximum number? I think Axel said it was 22, maybe 24, something like that.
The 26, 27 minus 1.
Okay, 26.
Is the maximum number of rays. And so optimal is, that's an interesting question. Depends somewhat on the problem. If you have a star in a box, we of course need to find out whether, I mean, it could well be that it is that 6 rays is all right.
Yeah, because I remember you saying in some pencil code meeting that maybe even 6 is enough for some kind of a trade-off between computing time and your accuracy. But I don't remember which pencil code meeting was that.
Yeah, right. We will revisit all of that, I think, now. Because now we have the problem with the sphere is it's a more difficult problem. And so I think we should be able to make that one at least work correctly. And so the results so far look very nice.
This is all star in a box or what?
Yes.
Yeah.
Okay, great. Yeah, really good. It was amazing that this bug was, after so many years.
Yeah, I mean, it's amazing. Actually, before this merging thing, we had these 2 different routines, and presumably they would have still been okay. It's just when we merged them, we didn't notice this anymore.
Okay.
I don't know,
So,
strange, right?
Actually, are there more questions? Oh, maybe one of mine.
So maybe one comment. So maybe it would be good then to have a sample of this somehow to put in the auto test, that now what you achieve is not lost.
I mean, we do already have auto tests with radiation. And they
but maybe then put in some more polarization in or something.
Yeah,
maybe that was the problem. Yeah, right.
My sample also has radiation, but it's not part of auto test. So,
so maybe that's, I just modify it that you have, as I said, radiation, polarization in X and Y and Z or whatever.
Right, exactly.
Because now you have achieved it, and then maybe 2 weeks later, someone just make a check-in, and then you have to find it out again. So it's good.
So actually, we now break for
just
Shohel last question.
So it's not one question. So it's just a comment what Axel was saying. So Axel, we also did do this radiative MHD convection simulations. So we also have this tau equals to 1 surface. So at some point of time, I actually calculated this tau equals to 1 surface and colored it with this vertical plasma velocity. So what I saw is like this, there are like this tau equals to 1 surface is not like a plane surface, there are curves. And I saw whenever the plasmas are going down flowing, there are like dips in this tau surface, and this tau surface colored with this vertical velocity looks very well. It looks very consistent with the observation, and those plasma blobs are like really nice looking plasma blobs are there. Still, I thought like it's okay with this radiation profile we are getting the result, but I'm not sure with these corrections how these results will change. But I checked that. It looked pretty well, even with that bugs. I'm not sure how that changed now.
Yeah. No, I think that would agree with my experience. You're probably lucky then that it would not show up. So when I looked at the tau equal 1 surface in my earlier runs, where I have just radiation in the Z, I mean, in all directions, of course, but mainly stratification in the Z direction. So these were Cartesian Z stratified runs. Yes, then the tau surfaces, tau equal 1 surfaces were of course corrugated because there's convective flow and everything was non-uniform. And but then there was no pattern from the processors.
Right. Our experience too.
I have to also check this explicitly.
But then we had optically thin cooling also, so that may be
right.
Yeah, so it's interesting problem.